In this work, we propose a method for safe feedback motion planning using learned dynamics models that leverages learned feedback controllers based on contraction theory. Provably safe algorithms for motion planning with learned dynamics models are critical for deploying robots in the real world. However, by naively planning with the learned dynamics without considering bounds on the model error and the resulting trajectory tracking error, the system may become unsafe. This is because the planner can, and will, exploit errors in the learned model to generate plans which cannot be tracked in reality. In this work, we develop a method for finding and using these error bounds in order to plan trajectories with the learned dynamics that can be safely tracked in execution on the true system. Our method consists of three major components: learning, verification of the learned components, and planning. First, we learn a control affine dynamics model from data, and then learn a contraction-based feedback controller that can stabilize the learned system around nominal trajectories. We then analyze the quality and correctness of the learned model by estimating several relevant constants that depend on the learned model and the controller, and which are valid over a domain D, which we will ultimately use as a trusted domain for planning. These estimated constants define the size of a trajectory tracking error tube around the nominal trajectory. Based on the size of the tracking error bound, this can then inform which domain D we should choose for planning, and this process iterates. Finally, we can use the learned dynamics, learned controller, and the verified tracking error bound to plan safely within the trusted domain D. Let's break down our approach in more detail. We first focus on the learning component of our method. Here, our goal is to learn a model of the unknown dynamics from a dataset of dynamic samples, and then obtain a trajectory tracking feedback controller, which is contracting for this learned model. In particular, we learn a control affine approximation of the unknown dynamics, where F and B are both represented with deep neural networks. We then learn a control contraction metric M of X for the learned dynamics, where again M is also represented with a deep neural network. If the B in the learned dynamics satisfies a certain sparsity assumption, then we can use a contraction condition which enables us to directly recover a feedback controller from the metric M of X. If the sparsity assumption fails to hold, we can use a different contraction condition to learn the feedback controller in tandem with the contraction metric M of X. In this case, the feedback controller will also be represented with a deep neural network. In the next section of our method, we seek to analyze the quality and verify the correctness of our learned model and controller. In particular, we wish to find a bound on the model error and on the trajectory tracking error within a region which is verified to be contracting, and then use this information to design a trusted domain that the system should remain inside during planning. Assume for now that the trusted domain D is given. We first derive a spatially varying model error bound within D using the Lipschitz constant of the error and the training error. We then derive a trajectory tracking error bound for a contraction-based controller which is subject to this model error description. This bound depends on obtaining valid over or under approximations of several constants. We provide a means to obtain probabilistically valid estimates of these constants, as well as a means to probabilistically verify that the controller is indeed contracting over the domain D. We can then use the size of the computed tracking error bound to inform whether or not we should redesign D to make it larger or smaller in order to make planning maximally permissive while also safe. Finally, we use the learned dynamics, the learned controller, and a trusted domain in order to plan safely. Specifically, for a given start and goal location within the trusted domain D, we wish to plan a trajectory using the learned dynamics, which can be safely tracked in execution on the true system. We can do this by imposing additional constraints on a kinodynamic RRT. We refer to our modified planner as LMTCD RRT. Our modification relies on growing trajectory tracking error tubes around any candidate extension within the planning tree, and ensuring 1. That the tubes themselves are collision-free. This ensures that the system will not collide when attempting to stabilize around the plan. And 2. That the tubes are fully contained inside the trusted domain D. This ensures that the tracking tube is in fact valid, since outside of D, our bounds are not verified and may end up underestimating the true tracking error. If these conditions hold and a plan is found, the system, in execution, will remain within D and collision-free when tracking a trajectory that is planned using this approach. Now we provide an overview of our experiments on safe planning with learned models of a 4-dimensional car, a 6-dimensional quadrotor, and a 22-dimensional rope. In the following, to demonstrate the need to both stay within the trusted domain D and to also use our Lipschitz-based model error bound when planning, we will compare with the following baselines. B1 remains within D, but computes tracking error tubes using a naive model error bound, assuming that the model error within D is uniformly bounded by the mean training error. B2 also remains in D and assumes the model error is uniformly bounded within D by the maximum training error. B3 can exit D and uses the naive maximum training error bound. B4 uses our Lipschitz-based error bound, but can exit D in planning. We first show our results on the car. Given training data, a subsampling of which is displayed here as black dots, we apply our approach to plan from the start to the goal in this figure. The legend here also applies to the following animations. This is the result using our method, LMTCD-RRT. The arrows here indicate the heading, and their magnitude scales with the linear velocity of the car. Recall that the solid lines are the planned trajectories, and the dotted lines are the executed trajectories. We can see that the system is able to closely track the planned path and execution on the true system, and remains well within the computed tracking error tube. In contrast, the baselines do not all fare so well. While B1 and B2 stay within their bounds in this case, this will not hold for the higher dimensional examples. On the other hand, B3 and B4 exit their tubes and end up crashing. To clarify, B3 and B4 exit D by moving far from headings and velocities seen in the training data. Next, we visualize one set of results for the quadrotor system. This is the result of our method. The arrows here indicate the angular position of the quadrotor. As in the car example, we see that the system is again able to closely track the planned path and execution on a true system, and remains well within the computed tracking error tube. The baselines struggle more in this case. B2 fails to find the plan altogether because by assuming that the model has the maximum training error uniformly across D is too restrictive. The other baselines all exit their computed tracking error bounds near the end of execution. Here's another set of results on the quadrotor system for a different start and goal pair. Like before, our method finds a trajectory which can be tightly tracked in execution, and the executed trajectory again stays far from the boundary of the tracking error tube. In contrast, the baselines struggle more. B1 remains safe, B2 is again infeasible, B3 and B4 exit their computed tracking error tubes and crash into obstacles as a result. Finally, we visualize our results on a 22-dimensional planar rope manipulation task. Controlling deformable objects is known to be highly challenging due to their infinite dimensional state spaces and a resulting high degree of underactuation. We consider an approximate rope which is represented by 10 rigid links and therefore 11 nodes. Our state representation is 22-dimensional as we consider the xy positions of each node to be part of our state. We assume that the head of the rope is velocity controlled. This resembles the setting where a robotic manipulator is grasping the rope's head. This gives a two-dimensional control space which encodes the commanded x and y velocity components. Our rope dynamics are simulated in MuJoCo, which captures the complex interactions between the rope and the ground and between adjacent links. Our task is to steer the tail of the rope to the goal position while ensuring that the rope remains collision-free in the process. This is highly challenging since we can only indirectly control the tail by moving the head and by using a model of the remaining links to determine the tail's motion. Our dataset is comprised of 3 demonstrations. Demonstration 1 is a counterclockwise elliptical motion, animated and shown in full on the left. Demonstration 2 is a vertical motion, and demonstration 3 is a horizontal motion. We also collect variants of demonstration 2 and 3 at different velocities, and collect perturbations around the demonstrations to train the feedback controller. We first visualize the result of our method. We animate the trajectory on the right and show the full execution on the left. We also plot the path of the tail, traced out by the planned and executed trajectories in orange and blue, respectively. As we see, the plan remains close to motions in the demonstrations, stringing together parts of the counterclockwise loop with horizontal and vertical segments. In doing so, the system reaches the goal successfully. Note that our planner does not simply move the rope down into the right between the obstacles. This is not because of suboptimality, but rather because the motion for doing this is nowhere near the training data. This causes the tracking tubes to grow larger than the size of the passage between the obstacles, thus blocking such a strategy. In contrast, all baselines will fail. We show B1 and B2 first. Recall that B1 remains in D, but uses the mean training error as a disturbance bound. This causes a severe underestimate of the tracking error, as we can see here by the imperceptibly small tracking tubes for B1. This leads to plans which get too close to the boundary of D, which enables model error that is seen in execution to eject the system from D, causing it to go unstable when the controller attempts to stabilize the system in regions that it has not been trained on. B2, on the other hand, uses the maximum training error as the uniform disturbance bound. This can be restrictive, as seen in the previous examples, but is also not safe, since the model error in D can actually exceed that which is seen on the training set. This also leads to an underestimate of the model error, leading to the same unstable behavior seen for B1. B3 and B4 also fail. Recall that B3 exits D and uses the maximum training error as a disturbance bound. As a result, B3 returns a plan which goes very far from the training data, attempting to perform a clockwise maneuver around the obstacle even though such data was never seen in training. We can see that the planned trajectory is highly unrealistic, reflecting the fact that the dynamics model is not trained there, and thus we cannot expect it to be accurate there. As expected, the controller fails to stabilize around this unrealistic plan, and the system goes unstable. On the other hand, B4 exits D and uses our Lipschitz-based bound, which may not be accurate outside of D. Despite this, our bound still grows rapidly when deviating from the training data. This forces B4 to remain near the training data until it moves through the narrow passage between the obstacles, after which it moves away from the data. The controller works well up until this point, where it fails to stabilize and the system goes unstable. In summary, we present a method for planning safely with learned neural network represented dynamics models, which scales to high-dimensional under-actuated systems. To achieve this, we bound the model error that the system may see within a trusted domain around the data, and then derive a bound for the trajectory tracking error for a contraction-based controller when it is subjected to this model error description. We then use the tracking error bound to guide a kinodynamic RRT-based planner to return plans which can be safely tracked in execution by the controller. Thanks for your attention, and for any questions, I can be reached at this email address.